So now we turn to groups, which we're going to view as metric spaces, actually more precisely associate metric spaces to groups in a not quite canonical way, which lets us study geometric group theory. That is, they become geometric objects in this. Okay, so suppose now here G is a group and S is a finite generating set. So this means that we have assumed that our group is finitely generated. Yeah, so it being a finite generating set means that each G in G can be written as a product of the generators and their inverses. So it can be written as G equals S1 plus minus 1, etc. So Sn plus minus 1, where S1 and Sn are generators. Okay, so I'm not taking symmetric generating sets. Sometimes by convention we assume that the inverses are also in S, and so then you don't need to put plus minus 1 here. Okay, and so each element can be written in this way, what is called a word metric. But so far we are just looking at the corresponding norm is the following. So definition of the norm of G is the smallest n such that there exist S1 Sn in S, and let me be precise, epsilon 1 epsilon n in minus 1 1, such that G is S1 to the epsilon 1, S2 to the epsilon 2, Sn to the epsilon n. Note, I'm not saying this is the shortest expression. I mean, it is a shortest expression. So it's the smallest n greater than or equal to 0, such that we can find appropriate generators. By the way, these can repeat. Si may not be distinct, and usually are not. In fact, S is a finite set, and n may be much larger than the cardinality of S. So by pigeonhole principle, they will repeat in that case. So usually they don't repeat, and usually they do repeat. So the smallest n for which you can find such an expression is called the norm of G. It's telling you the length of G. Some sense. So let me have just a convention, which is a standard one. E is the empty product, or I should put it the other way around. The empty product is the identity. In the case of any associative product, we will want to make these conventions. Okay, so of course norm E 0. Let's look at some properties of this. So properties of this norm function. Okay, sometimes we'll put norm S to emphasize it's dependent on S. Well, first of all, norm G is non-negative, with norm G equals 0 means that G is an empty product. And this happens for the identity and only for the identity, if and only if G equals E. And B, second property is that norm of G times H equals, need not equal, it's less than or equal to norm G plus norm H. Now this is a simple fact, but just to get used to the definitions, let me give a sketch of a proof. As, let's say norm G equals N and norm H equals M, then there exist S1 Sn in S and T1 Tm in again S, such that G can be written as S1 where plus minus 1, Sn plus minus 1. I won't put explicit notation for the sign, and H can be written as T1 plus minus 1, Tm plus minus 1. So this means you just multiply them together. And what you get is G1 S1 plus minus 1 Sn plus minus 1 T1 plus minus 1 Tm plus minus 1. What does this say? That is GH can be written as a product of M plus N generators and inverses of generators. Inverses of generators, what is the consequence of this? Remember what is the norm? Okay, so the norm is the smallest way in which you can write it as a product. Now you can write it with N plus M, and so you can perhaps write it with even fewer or perhaps not, but whichever way it is, norm of G plus H is at most N plus M, which is the sum of the norms. Okay, so we have seen, well, these are the usual norm properties. We also see another simple fact, which is norm G is less than or equal to 1 if G belongs to S is a generator. This by definition it can be written as one letter. Oh, I forgot to add, let me call this D. C is the more fundamental property. It's that norm G inverse equals norm G. So I'll call this an exercise. You should do this exercise to get used to what the norm is. If I invert it, well, then I have the same norm. And so A, B, C are the main norm properties, but we have an additional property, norm G is less than or equal to 1 if G is in S. By the way, it seemed as if it's equal to 1, but I haven't ruled out identity being just included in S.